For gravitational and electric fields, you will see again that your information sheet is important because I'm going to summarize it at the end, but you will see that the first equations on your information sheet helps you with your laws. The second equations on your information sheet helps you with the definitions. And the third one, the third column helps you to describe the describing questions. So please remember that your information sheet is super important. We're going to start by looking at gravitational fields, but you must remember that fields are fields and they all behave very similarly. The only thing about gravitational fields is that it's always going to be an attraction. So if you look at Newton's law of universal gravitation, you will see that it says that every particle with mass attracts every other particle, obviously also with mass, and that force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, you've done this in detail in class, but if you look at the equation, then you can see there's two masses. So a force is always between two objects, and you must remember Newton's third law. The force of mass 1 on mass 2 is going to be equal to the force of mass 2 on mass 1. So that means that in your equation, when you look at your information sheet and the question is asking for force, highlight force, because then you know there's going to be two masses because it's a force between two things. And it also helps you to describe the law because the force between these two masses directly proportional, so you go to the top of the line, to the product, there's a multiplication sign, to the product of the two masses inversely proportional to the distance between them squared. Now, you also need to be able to draw these fields, and for all the topics, for all the fields, you're going to have to be able to draw the fields. Now, just remember, gravitational fields are always towards the center of the mass. In this case, it will be the Earth. And keep it simple. Make sure these lines do not cross. I always say one at the top, one at the bottom, one at the left, one at the right, and then just do one in between. That's enough. You don't have to go and draw 1,000 lines because the chances then that they're going to cross are big, and then you're going to get no marks for it. So please remember that. Now, we also have to look at the masses involved here. So if we look at the masses involved, if the one object is the Earth, which it often is, or another planet, remember, we're now generalizing, we are not only looking at the Earth. Now this force, this F, is the force of gravitation. It is the gravitational force. And you will remember Fg is also the weight. You even get that on your information sheet. So Fg is the weight if you are on Earth, because if I am sitting here on top of the Earth, I am attracting the Earth is attracting me, and this gravitational force is the force between the two of us. So please remember that if they're asking for the weight, they are actually asking for the gravitational force. So don't think it's something that you've got missing information here. Now, what you also learned in grade 8, I think, is that when we want to calculate the weight, we can also say that that is the mass times by g, the gravitational field strength. So that brings us to the gravitational field strength, and we have to actually quickly look at that. Now, how do we define the gravitational field strength, or actually any field? You'll see they're all the same. If I look at my equation, so I said to you the second ones here help us with the definitions. So if I look here, small g is the gravitational field. First column, forces. Second column, fields. So this is gravitational field, and if you look at the equation, it tells you that it's the force per unit mass. So you'll see in the definition, it's the force acting per unit mass. And there you have your definition as well. But now what is this force? Because we're talking about a gravitational force. So instead of that Fg, or instead of the F, remember I can put Fg or even W. Now I'm hoping some bells are going off that you can see, and I'm sure you have done this in class as well, but you can now see that we have in the middle here, we have G, M1, m2 over r squared. Now let's do what your information sheet is doing. And they actually make one of the masses a capital M, because that will be then the Earth, and the small m would be me sitting here on the surface of the Earth. When you worked with W equals mg, that was the mass of the person or the mass of the object. So these two m's, can you see what's happening? They're the same m. So they actually cancel out. So we end up with an equation for gravitational field that is G m over r squared. Now, this field is created by this object. So you need to be very careful. When am I using which equation? Because now you've got that G equation and you have the one with F, force per unit mass. So there's two equations. So now which mass am I going to use in which circumstances? So if they're asking you, and now we need this little diagram, yeah? If they're asking you about the field created by the Earth, then this equation tells me that this is, remember that was the Earth. So the field created by the Earth, the big M would be the Earth. So the object responsible for the field, for forming the field, is going to be the capital M. The object experiencing the field, so this little object here, whether it's on the surface of the Earth or not, that little object there is experiencing a force. So that's going to be this mass here is going to be the small mass. And now if I change that back into what you are used to, remember this force is Fg. So you can see that G is equal to W over M that you've been using forever. W is equal to mg. Same thing. So now we can go and look, why are we sometimes saying that G is the gravitational acceleration? And why are we sometimes saying that G is the gravitational field strength? Because it is actually really both. And that's an important point that's emphasized in your SAGs, you will see. Now, if we look at this, if we are on Earth, so I'm just going to use Earth, and you know that the gravitational field on Earth, so the force per unit mass, is equal to 9.8. Now, please, if you are in fields, use the correct units because it's force per unit mass. So it means it's newtons per kilogram because we are dealing with fields. It's the field strength. So it's you show that you know your definitions. So that's the one. But now we also know that F net equals ma, according to Newton's second law. So if I have a 1 kilogram object, let's just quickly look at it. So this would be the force per unit mass. So that means that is 1. If I put a 1 in the place of the mass, I'm going to say 1 times by A. And I've just said that the force per unit mass is 9.8. So this is equal to 9.8 newtons per kilogram. I'm just going to leave the unit out for now. And then you can see that the acceleration is then also going to be 9.8 meters per second if we are second squared, if we are close to the surface of the Earth. So please remember that these equations are equivalent. So now we say gravitational acceleration, gravitational field. So we use a G for each of them because the size is exactly the same. But when we speak about acceleration, we can use the unit meters per second squared. When we're speaking about the field strength, we rather use the unit Newton per kilogram. So now if they asked you for the weight on any other planet, please just know that it's still the force of attraction and you're just going to stick the masses into your equation and you're going to calculate. So you will now see that we basically covered everything in the SAGs here. So let's just go and double check. So why is it letting me down now quickly? There we go. So I'm going to just quickly look that we've done everything, and you can see state Newton's law. You're going to use your first equation. Define the weight, you're going to use your second equation, the force per unit charge or per unit mass. And if it's on the earth, it's the earth exerting a force on any object on or near its surface. So that's specific to the earth, but remember it could be for any other planet as well. Describe gravitational field. That's the area around the earth. So if you were going back here, it's the area around the mass where something else will experience a force. Then we derived this equation. Basically, we said gravitational field is the force per unit mass, and then from there we got to this equation. So these two are equivalent. Please remember that gravitational field and acceleration due to gravity. We just spoke about those. We must be able to calculate a gravitational force, and remember that is just the weight. It's Fg. You use the two masses. And you can also use the gravitational acceleration if they give you the mass of the planet. Oh, we haven't spoken about mass and weight, and that is always one that a trap in a multiple choice that people fall into all the time. So let's just compare those quickly, because mass is a scalar. So mass has got to do with the chemicals that I am made of. So if my mass is, I almost said 20 kilograms, 60 kilograms, it's got to do with the carbons and the waters, lots of water, hydrogens. But if you look at the periodic table, if you add up all those masses, that's the mass of the substances that I am made of. So whether I go to Earth or to Pluto or to Mars or to Durban, my mass is still going to be 60 kilograms. It never ever changes, and it doesn't have a direction. It's got to do with the chemicals that I'm made of. And it's measured in kilograms. The weight, remember now, the weight is Fg, and that is equal to that whole equation there. And it is a force per unit mass. So it's a force. So gravitational, or it's the force times by the mass eventually, but it's a force. So we measure the force in newtons, and it has a specific direction. It's always to the center of the planet. So this can be different on different planets. But we cannot have different masses, because the chemicals, we didn't lose an arm or something. We still have the same chemicals that we made of, so the mass will stay the same. But the weight, because it depends on G, which is the same everywhere, M1, M2 over R squared. These M's, one of them is the Earth, and then U. So this will just change if it's another planet, but it's still a gravitational force, and it's still going to be to the center of that planet. Now, ratio questions often come in the field section as well, and I will look at that in detail in the next video. But just remember that it works exactly the same for gravitational fields as it does for anything else.